Okay, let's jump right into this explainer. We're going to uncover the massive, incredibly high-stakes global coordination system that's required to fix the internet when it suddenly breaks at the bottom of the sea. We tend to think of our digital lives as existing in this weightless, invisible, wireless cloud, right? But the reality is highly physical, deeply submerged, and honestly, constantly under threat. It all starts with a super simple, everyday action. You press play on a stream, and a data request races across the globe. Now, we should be really precise here. While submarine cables carry the vast majority of intercontinental connectivity, not every single internet action crosses an ocean. I mean, if you're just emailing your neighbor, that traffic stays local. But when you request data hosted on a server on a totally different continent, that request travels through an optical fiber thinner than a human hair, resting completely unprotected in the mud of the deep ocean floor. And occasionally, without any warning at all, that physical path gets severed. The breakdown of exactly why these breaks happen tells a pretty fascinating story. You might immediately picture, a shark bite or a massive underwater earthquake, but the truth is way more human. Look at the numbers. 44% of faults are suspected fishing or anchoring, with another 28% confirmed fishing and 14% confirmed anchoring. The vast majority of this damage happens in shallower coastal waters, where maritime activity is really heavy. Commercial fishing nets and massive ship anchors are dropped to the seabed and dragged along with just immense force. When a heavy steel anchor snags a cable that's barely an inch thick, the cable literally doesn't stand a chance. It's almost entirely accidental, but the consequences are global. To understand how this gets fixed, we're going to trace the exact chronological handoffs of two parallel systems that wake up the very second that cable snaps. We'll cover 1. An ocean-deep interruption. 2. Digital triage and fault detection. 3. Mobilization and maritime constraints. 4. Grappling and surface recovery. 5. Splicing the spare cable. And finally, 6. Return to the seabed. Starting with Section 1, an ocean-deep interruption. When the connection actually snaps, the crucial point to realize is that the illusion of the wireless cloud just instantly vanishes, and heavy physical reality takes over. And this isn't some incredibly rare, once-in-a-decade anomaly. The global submarine network experiences an average of 200 faults a year. That's roughly 4 critical breaks somewhere in the world every single week. Because this is such a regular occurrence, just an enormous baseline of wear and tear, a highly structured response protocol is triggered immediately upon failure. Which brings us to Section 2, digital triage and fault detection. The moment of failure splits our focus, activating both a digital continuity network and a physical maintenance operation. These two tracks run completely simultaneously. On one side, we have System 1, digital triage. Network operators in global centers see alarms flashing, and they must instantly manage the disrupted capacity. They're rerouting terabytes of traffic to redundant protection paths where the network topology actually allows it, making split-second decisions to provide cascading failures. But keep in mind, redundancy does not guarantee invisible service. If multiple cables are damaged or alternate routes max out, you might still get that dreaded buffering screen. Meanwhile, System 2 wakes up. This is the physical repair track, a completely separate, heavily constrained operation that takes weeks to actually execute. But before a repair ship even starts its engines, the engineers on shore have to figure out exactly where to send it. They use this critical diagnostic tool called an optical time domain reflectometer, or OTDR. Think of it like this. They shoot a powerful light pulse down the broken wire from the shore station. When that light hits the physical break in the glass, the energy reflects back, exactly like shouting into a canyon and waiting for the echo. By timing down to the microsecond exactly how long that echo takes to return, they can calculate the precise distance to the fault in the pitch-black ocean. Moving to Section 3, mobilization and maritime constraints. Knowing exactly where the fault is, the cable owner must now activate their maintenance arrangement and dispatch a vessel. The sheer scale of what's required here is staggering. You can't just charter a regular cargo boat on a whim. These are $100 million purpose-built cable ships, like the Subcom Reliance class. They have dynamic positioning systems to hover precisely over deep ocean coordinates and are staffed by highly experienced marine teams. Inside the hull of these incredible ships are massive, room-sized drums carefully loaded with compatible spare cables. Now, this right here is a massive failure path. The technicians have to ensure the spare cable matches the exact optical fibers and mechanical strength members that were severed. If they load the wrong spare or a cable with incompatible power voltage requirements, the whole multi-million-dollar mission fails. And honestly, the delays can pile up before the ship even leaves the dock. Owners face severe bureaucratic bottlenecks. They have to activate private agreements, secure tricky permits in foreign territorial waters, and navigate domestic cabotage laws that regulate which ships can even operate in certain regions.
On top of that, mobilizing across an ocean to reach a remote fault can easily burn up to $2 million in fuel alone. Every single one of these constraints keeps your internet capacity choked just a little bit longer. Section 4. Grappling and surface recovery. Once the ship finally arrives at those GPS coordinates, the physical extraction begins. Because the water is typically way too deep for human divers, the crew basically has to fish for the internet. A specialized heavy grapnel is towed along the seabed to blindly hook the buried cable. Once they snag it, it's hauled to the surface under immense tension. They cut away the violently damaged sections, test the clean end to ensure it communicates flawlessly back to shore, cap it, attach it to a high-visibility buoy, and literally just leave it bobbing on the ocean waves. So what happens next? The ship leaves that buoy and carefully sails over to the other side of the break. They do the exact same grapnel trick, recover the second end of the severed cable, bring it aboard, test it, and strip away the remaining damage. Finally, they have a clean second end secured on the deck. Which takes us to Section 5, splicing the spare cable. This is where the heavy industrial maritime environment suddenly meets the sterile surgical environment of an operating room. Inside a highly controlled, dust-free jointing room, they perform the initial splice. This is arguably the most delicate part of the whole shebang. They painstakingly fuse microscopic glass fibers, literally thinner than a human hair, to a fresh drum of spare line. And they're doing this flawlessly while the massive ship is pitching and rolling in ocean swells. They also have to perfectly recreate the mechanical housing so the new joint doesn't instantly get crushed by the pressure of the deep ocean. Once that first connection is solid, the ship slowly travels back to the buoy, paying out the new spare cable as it goes. It grabs that first end we left behind, brings it into the jointing room, and they make the final splice. Sometimes, if the spare cable is really long, they'll even add a repair repeater, a powered device that boosts the light signal so your data doesn't degrade over the distance. Finally, Section 6, return to the seabed. The digital circuit is fully reestablished, but there's one last mechanical constraint. You see, you can't just lay the repaired cable back down perfectly flat. Because the replacement section had to be long enough to reach all the way from the seafloor straight up to the ship and back down again, the new cable is naturally much longer than the original line. So when they lower that heavy final splice back into the water, the geometry forces an extra loop, a coil of slack that will permanently rest right there on the ocean floor. Obviously, an exposed loop of cable on the seabed is a huge vulnerability. So to protect it, especially in shallow areas, they'll deploy a remotely operated vehicle, or ROV. It hovers over the cable and uses high-pressure water jets to blast a trench into the mud, safely burying the loop. After that, the crew meticulously documents the exact coordinates of this new route, sending the data to hydrographic offices so they can update maritime charts and warn future ships away. And that incredibly complex ballet brings us to our final takeaway. We almost always think of the internet as this invisible, magical force in the air, but it relies profoundly on the heavy, fragile physical world. That solitary repair ship out on the rough waves is really just the visible endpoint of a globally coordinated network of diplomats, digital operators, and engineers fusing glass in a storm. So the next time your video stream buffers for just a split second, ask yourself, how many engineers, diplomats, and sailors are currently scrambling across the ocean, fighting the elements just to keep your illusion of the cloud alive?